In this video, I'm going to show you how to model with geometric sequences. So here's our first problem. Suppose that in each minute, the temperature of your hot dinner decreases by 20% of the amount it exceeds room temperature. If the dinner is initially 50 degrees above room temperature, how many degrees is it above room temperature after 9 minutes? Okay, so why don't we just draw out the first few minutes to organize our information and get a sense of what this problem is asking. So we'll make a table with minute here, and then we'll have temperature on the other side. And that temperature, of course, will be the amount by which it exceeds room temperature. Okay, so it says the dinner is initially 50 degrees above room temperature. So that'll be our first temperature here. But that's not actually the first minute because no time has passed yet. The temperature after the first minute we get by applying this rule. It decreases by 20% of the amount it exceeds room temperature. So we have to decrease this number 50 by 20%. Alright, so let's think about that. Decreasing by 20%. It'd be a lot easier if we could just multiply some proportion of this number. And indeed we can. Decreasing by 20% is the same as taking 20% away from 100% of it. So 100% minus 20% is 80%. So that's what we're multiplying by every time. So we'll multiply by 80% to get to the next number. 50 times 80%, and 80%. Converting that to decimal, of course, that's just 0.8. So 50 times 0.8, and that would be the temperature at the first minute. All right, so now we're just applying that rule over and over and over again to get to the next minute. Minute 2 would just be multiplied by 80% again, really just times 0.8 times 0.8, over and over and over again. Okay. Now we see that this is a geometric series because there's a common ratio that we're multiplying by every time. To find how many degrees it's above room temperature after 9 minutes, we can just set up a rule for the nth term of this sequence. And we already know that for a geometric series, we have an equals, well here we want to start with a0 because the first term, 50, is actually at minute 0. So a0 then times r, the common ratio, to the power of n. And now we can just go ahead and fill this in. an equals a0. a0 is just 50. And then times the common ratio, that's what we're multiplying by every time. That's 80%, or just 0.8 as a decimal. So times 0.8, and then to the power of n. And in particular, we're interested in after 9 minutes. So we plug in 9 for n. A9 equals 50 times 0.8 to the 9, and we can just go ahead and compute that on our calculator. The result is that we get about 6.71. So this is how many degrees it's above room temperature after 9 minutes, 6.71. Alright, here's another problem for us. Bacteria in a lab are subjected to a chemical that causes them to denature. And initially, 6,400 bacteria are healthy, but each day the number of healthy bacteria is halved. How many days will it take for the population of healthy bacteria to shrink to 100 bacteria? Okay, so again, let's start off with a table. We'll have days over here on this side, and then we'll have bacteria, number of bacteria, on this side. Now it says that we start out with 6,400 bacteria. So 6,400 we put over here. But that's not on day 1, that's on day 0, because after a single day has passed, the population has halved from that. So this is at 0 days, this is our starting number. Okay, now each day the number of healthy bacteria is halved. So that's what we're going to be multiplying by to get to the next day, times a half. And we can already see that this is going to be a geometric sequence because we're just multiplying by a half every single time. So let's go ahead and set up a formula for the nth term. Now we know that the formula for the nth term of a geometric sequence relative to a0 goes like this. an equals a0 times r, the common ratio, to the power of n. So in this case, we have an equals a0. a0 is just 6,400 because that's on day 0. That's the initial amount. So 6,400. And then times r. r is the common ratio, so just what we're multiplying by every time. So that's a half here. So times a half to the nth power. Okay, and we want to see how long it'll take for the population of healthy bacteria to shrink to 100 bacteria. So we want to find the value of n for which an is 100. So we can go ahead and set that up. 100 equals 6,400 times 1/2 to the n. So why don't we first divide by 6,400 on both sides? That way we get 100 over 6,400 is equal to 1/2 to the power of n. And we can simplify this fraction a little bit. Divide by 10, and that's just like canceling these zeros. You get 10 out of 640, and then you cancel the next set of zeros. So just 1 over 64 is equal to 1/2 to the n. Now let's express this a little bit differently. So this is 1 over 64 is equal to 1/2 to the n. Well, 1/2 to the n is the same as 1 to the n over 2 to the n. And 1 to the n is just 1. So we just have 1 over 2 to the n. Okay, so 1 over 64 equals 1 over 2 to the n. Well, that's just asking for what value does 64 equal 2 to the n? If the numerators are the same, then the denominators also have to be the same. Let's continue this over here. Now we know that 64 is just 8 times 8. So let's write it like that. 8 times 8 equals 2 to the nth. And we know that 8 is just 2 to the third. It's 2 times 2 times 2. So this is 2 to the third times 2 to the third equals 2 to the n. And 2 to the third times 2 to the third, well, if we're multiplying 3 copies of 2 by another 3 copies of 2, then we have 6 copies of 2. So 2 to the 6th equals 2 to the n. And there we see that 6 equals n. So that means that it takes 6 days in order for the population to shrink to 100 bacteria. Here's a final example. Abigail invests $P at 6% annual interest rate. After 4 years, her investment is worth $8,000. How much will it be worth after 14 years? Okay, so this is an interest problem, and so that means we're multiplying her investment by the interest rate every year and adding that to the previous amount. So we know that this is going to be a geometric sequence problem, and so why don't we start with our template. an equals a0 times r to the n. And now let's look for the information to plug into this formula. So how about a0? a0 is the initial amount, and we know that Abigail invests $P as the initial amount. So we can plug in P for a0 here. Of course, that's not so helpful because we don't know what P is, but that's all right. Let's just continue plugging in information. So P times r to the n. And what is r here? Well, r comes from the 6% annual interest rate. Each year is 100% plus an additional 6% of the previous year. So that's 106% of the previous year, and in decimal, that's 1.06. So r equals 1.06. So 1.06 to the nth power, and now we've got our formula here. Now we could try to plug in n equals 14 to get the amount that it's worth after 14 years, but one issue here is that we don't know what P is still. So we need to figure out what is P before we go ahead and plug in n equals 14. And to do that, we can go ahead and use this information. After 4 years, her investment is worth $8,000. That tells us that when we plug in 4 for n, the result should come out to 8,000. So 8,000 equals P times 1.06 to the fourth. And now this is an equation that we can use to solve for P. So we'll just go ahead and divide both sides by 1.06 to the fourth. So 8,000 over 1.06 to the fourth is P. So doing that on our calculator, we see that P is equal to $6,336.75. Now plugging that back into our formula, we have that AN is equal to $6,336.75 times 1.06 to the nth power. And now we're in a good position to go ahead and plug in n equals 14. So we do that, plug in n equals 14. A14 equals $6,336.75 times 1.06 to the power of 14. And we punch that into our calculator. The result is $14,326.78. So that's our value A14. So that is how much it's worth after 14 years. $14,326.78. Now we know how to apply our knowledge of geometric sequences to solve some real-life word problems. In the future, we'll learn even more about geometric sequences, such as how to quickly find the sum of many terms in a geometric sequence added together.